We have studied the two types of magnets in our past videos: permanent magnets and temporary magnets. Do you remember them? This is how one can define them in simple words. Please take a moment and go through these definitions. We will talk about the temporary magnets first. These are magnets that retain their magnetism only for a short amount of time, or only until they are kept under an external magnetic field. When removed from the external magnetic field, they lose their magnetism. We have seen the two easy processes used to make temporary magnets. We used objects made up of ferromagnetic material such as an iron nail and an iron bar. What do we know about magnets? We know that a magnet attracts magnetic objects like iron and attracts or repels other magnets. Do you know what this property is called? This property of magnets to attract or repel is called magnetism. Look at the example we saw. What is happening here is that the two objects are acquiring magnetism through their processes. So these objects weren't magnets. They acquired magnetism. This process through which any non-magnetic object acquires the property of magnetism is called magnetization. Yes, magnetization. This can also be defined as a process to magnetize any non-magnetic object. So in these processes, we are magnetizing the ferromagnetic objects. Now there is one more way in which we can magnetize these objects. And that is by understanding that electric current generates a magnetic field. First, let's enlighten ourselves about this. In 1819, there was a scientist named Hans Christian Ørsted. He found out that if you keep a compass near a current-carrying wire, then the compass needle deflects to some extent. Yes, understand this well. When current passes through this wire and we keep this compass near that wire, the needle will deflect. This will not work if the current in the wire is feeble. However, in that case, if we remove a part of the insulated coating and keep the compass near that region, you will see the deflection. Now we know for a fact that if we keep this compass at rest away from any other magnet, then it will align itself in the direction of the Earth's magnetic field. That is, the red part will point in the north direction, while the other part will point in the south direction. What will happen if we bring any magnet near this compass? Well, if we bring the north pole of a bar magnet near the red needle, the needle will show deflection. The needle now aligns itself in the direction of the magnetic field of this bar magnet. We know that in a bar magnet, the field line emerges from the north pole, curve around the magnet and end at south pole. So if we move the compass in the direction of the magnetic field, then its needle will also align itself in the direction of the field. With this knowledge in mind, let's go back to our copper wire. Here, the electric current in the wire produces magnetic field around the wire. Or in other words, the wire becomes a temporary magnet. This is the reason that the compass needle deflects when brought near this wire. But how exactly will the compass needle align itself if moved in the surrounding? Or in other words, what is the direction of the magnetic field produced by electric current in the wire? Keep watching our videos to know the answer.